I'm really happy to be here, so thanks for having me. Thanks, Spencer, for the introduction. The topic I chose for today is about full waveform inversion, which is a geophysical imaging problem. And no worries, I will not focus on the geophysical part. I just want to use it to show you what we in the optimization community and inverse problems community can already do with the tools that this community has put together, which is quite impressive. And I also want to use it to show you a few ideas that we have to distribute and parallelize stuff. Hopefully I get good feedback on that. And also motivate what's, in our opinion, a bit missing right now or where we want things to be going. Okay, so let's start. First, one slide about us. So the team is Eldad and me. Eldad couldn't make it here today, so I'm very sorry about that. We are well known with our GitHub usernames. I learned that yesterday, that it's essential to have these on the slides. If you Google these names, you will see that we are not really very active on GitHub, but every now and then there are a few discussions that we start, and actually I think we have one or two contributions to base 2 in this process. But a little bit about our interests. So Eldad is based at UBC in Vancouver, where I did my postdoc under him. He's an industrial research chair in geophysics, mostly electromagnetics, and his major interest is geophysical imaging. So he's in the Department of Earth and Ocean Science over there. So me. I'm based at Emory. I'm interested in inverse problems and solving them. I've done a lot of work in medical image registration, which is a specific image processing problem. And I would say my focus is numerical optimization, numerical linear algebra, and some things that really Julia is heavily based on. And yeah, this is why I appreciate that. So what we like about Julia and how we work. So both Eldad and me, we like to explore new things. So we see a paper, a nice idea, a new algorithm. We want to try it very rapidly. So this already rules out every compiled languages and languages that give us a big overhead. What we also like is we supply code, either to the industry, but also to other researchers. So for instance, my medical imaging code is freely available and is used by a few people. And our thinking, when we think about algorithm, is strongly based on linear algebra. So what we really want and what we really use is a SPY command, is an SVD command, and other commands that really give you insight about your problem at hand. So far, we are really MATLAB persons, because MATLAB does these things really, really nicely. Okay, we've been over decades we've been coding in MATLAB, and we've been really happy with that. So what made us change to Julia? Why am I here? One thing we want to experiment with, and this is essential in the applications we're interested in, is parallel computing. Okay, so ideally we would like to have a code that we develop on a single workstation. So we are not really. I'm not the type that develops everything via VI on a remote server. I like this machine. I like to develop code on this guy. But eventually, people would want to use it on a small research cluster, on a cloud or web service. So this would be really interesting, on heterogeneous architectures, and on a supercomputer. So this would be the dream, to have one framework, and this is what our experience is Julia already can do. To support a pipeline for that. And yeah, Patrick Sanan will actually give a talk later on about how to make it work on the supercomputer. We also like that Julia is a real language. So, well, for one very small reason. Okay, we like to hack, and we like to hack built-in functions. Because sometimes it allows you to do things that would either be very inefficient or impossible in other languages. So we had one example where we have a big matrix, and we want to, for preconditioning, there's a preconditioner called SOR, where you want to ignore, for instance, the lower triangular part. Okay? So how do you do that in MATLAB? You take the matrix, you duplicate the memory for the upper part, for the lower part, and you do backslashes on either of them. Okay? In Julia, you don't have to duplicate your memory. You just hack the upper triangular solve, add an if statement, ignore the other stuff. Done. Pretty efficient. So this is something that actually makes a difference in our applications and that we really like about Julia. Of course, we like the just-in-time compiler because it gives us flexibility. I mean, we've survived in MATLAB for long enough, so we know how to vectorize almost everything, but it always takes twisting your head. So here we have the flexibility of writing for loops. And eventually, we would like to close the gap between research and application. Because in Eldad's group, people are actually translating MATLAB code to Fortran before it gets delivered or applied to really big problems. Okay, so what's the agenda today? So it was just setting up the context about what I'm doing. So I want to give a brief introduction to FWI, full-waveform inversion. I'm not going to spend too much time on this. This would have been Eldad's part. Then I'm going to zoom into numerical optimization in Julia and show you a few examples how we code FWI first serially and then how we distribute the stuff over frequencies to make use of more workers that might be available. Okay, so FWI has a few components. For those that are familiar with inverse problems, they know that there will usually be a forward problem. There will be some misfit functions that measures how well you're doing, how well your parameters you want to estimate fit the actual observations. There will be some regularization. Then there's some optimization, and in the end, you want to look at some nice pictures. So these are the few blocks. I'll briefly sketch over them one by one. So this is how the general outline looks like. So this is the model M of the velocity. So basically, you want to look into the subsurface, and you want to explore material properties over there. There are many applications of FWI, but it's an indirect thing. You don't want to dig a hole. So you take some measured data. In this case, you have seismic waves you plug into you put into the ground, measure some response, record that. That's the data you work on. That's the unknown model. And based on this data, you want to get the model. Okay? So what do you need to do? You consider the following optimization problem. So phi will be the objective function. There's a misfit term and a regularizer term. M is the unknown model. Each M gives you a U, which is obtained by solving a PDE, by doing a simulation, how the waves propagate, and you compare it to the data. Okay? So U of M are the fields that depend on the model. S is a similarity measure, and R is the regularizer. That's a big, big picture. I will focus on how to get U of M, so how to solve the PDE, and then I'll show you some code how to do it in Julia. Okay, so what forward operators are there in FWI? Usually, I mean, this is the simplest one, and the one we're dealing with today is based on Helmholtz equation, so about a complex technology PDE. And that's actually all we need for today. There are more complicated models, and the goal is to have a code that is modularly extensible. Also one reason to go to JuliaCon to learn that. But we will focus on the very basic thing. So in a few slides, how to solve Helmholtz equations in 2D. So we really want to make our life simple for today. So that's the animal. We will assume that the density is constant. Okay, so this guy will go. The kappa also will go, and in the end, we will simplify it to this system. So that's the Laplacian of U, the field. Then there's the omega square. So this is the frequency, and we will later on have many frequencies, each frequency giving us a different PDE, and we will parallelize over the frequencies. And then we have a mass matrix here in the back, which basically is some version of the identity. And Q will be the source, so where we propagate the waves into the ground. And we'll use some finite difference or finite volume scheme to discretize the operators. Okay, so how does that look like? We have to make some choices where to put things. And usually what we do, we think of the material properties being in these red points in the cell centers, because we think of them as piecewise constant. And on the nodes then, we put the fields, okay? And then if you do some finite volume tricks, you can derive some good discretization. And we put some absorbing boundary conditions to help with the intermission to infinity. Okay, so what we need to do, we need to have some differential operators. That's the PDE part of the talk. So we want to solve Helmholtz PDE, so we better code up some gradient. And the gradients now, we have to keep in mind that we have the blue quantity we want to take derivatives of. So we will have some staggered discretization of the finite differences. So it brings us from the nodes to the edges. That's quite important conceptually. You can think of it as a central finite difference based on the different locations. It's second order accurate. But just keep in mind that the x1 derivative is on a different scale on a different spot than the x2 derivative. Okay? So how to code it in Julia? Finally, some code. It's pretty easy. You code a ddx, which is a generic one-dimensional derivative. Okay? And there's an SP diag M. You have -1 and 1. You put them on the diagonal and right beside. And you get a matrix from n plus 1, that's the number of nodes, to the number of cells. Okay, so that's a 1D derivative. You can test that this is working, but that's homework. And then, once you've coded it in 1D, that's the nice thing of dealing with a regular mesh, you can just use the following ideas to get it to ND. So think of the field being organized in a 2D array, right? We have a two-dimensional problem, so we can think of it as a 2D array. And what we want to do is first we want to differentiate it in this direction. So we multiply it with the 1D interpolation from the left. And it's very innocent. I just add an identity on the right side. Okay? Doesn't do anything. If we want to take the x2 derivative, what I'm going to do is I'll take my u, still a 2D array, and I'm multiplying it from the right with a transpose of the 1D derivative. Okay? And just because it's so innocent, I put an identity now on the left side. Okay. So this is how you code a gradient. Not quite, but all you need to do is you need to use the Kronecker product rule. So when you have something A, U, B transpose, right? This was exactly what we had. You can build the Kronecker product between B and A. In our case, it's always one 1D derivative and an identity matrix, and multiply it by the vector u. Right, so that's kind of really nice in our codes, because then we once built this thing, and then we can keep u as a vector. We don't have to go from left to right. All the linear algebra part becomes much easier. And yeah, then we put this into a function called getNodal but here you can see, well, here that's a costly part. The gradient we get by applying Kronecker product and a vcat. This used to be really, really slow 1 year ago when we started in Julia, but thanks to Viral, I don't know if he's here, this like overnight got a speed up factor of 100 or so. And so this is actually faster than in MATLAB, at least in our experience. So this is pretty cool. It's one really nice example how Viral and all the other people in the Julia community helped us. Okay, so this is how you code a gradient. Now you can do it also in 3D. I'm skipping over it. It's just adding one more Kronecker product outside. Okay. Well, then the divergence, well, you just transpose the gradient and put a minus sign in the front. That's not only practical, but also pretty nice to keep symmetry. And just keep in mind, we have lazy boundary conditions here. We didn't work too hard. Okay. So, but this is then how I discretize a Laplacian in Julia. So all you need to do is a 1D derivative. Well, just a quick word. We have the material properties in the cell centers. We kind of need to put them to nodes. So there will be some average matrix that you can also build in 1D and then use a Kronecker product, which is done here. So here you have a +1 and +1, some boundary conditions, both to a half. Then you Kronecker things together and you get the transmission from the cell centers to the nodes. Okay, so now let's dive more into really Julia. we're not so fancy developers, I would say. So we try to avoid types every now and then. We just use them if they are really necessary. So this was the first type I could agree with Eldad to have. The type is called a regular mesh, because this was what we are talking about. And this is a small description of it. So usually we put the domain size, the cell width, the dimension of the problem, and some other things. And what I want you to focus on here, so we have an n-lab, which is a nodal Laplacian, a CC-lab, and an AN. So these all are sparse matrices. We decided to put them into this type because then we have kind of a persistency, an option to put something to it and not recompute all the Kronecker products all the time. Okay, and we have some constructor. So then, when we want to get a nodal Laplacian, what I'm going to do is I use this, get nodal Laplacian of a mesh. We use multiple dispatch. So for a regular mesh, it knows exactly what to do. It first checks if it already has computed the Laplacian. If not, it builds this thing. It's the same code that I showed you before, plugs it into this field, and then returns it. So that's one command that we use for all the sparse matrices because they are costly to build, but nice to have. Okay? And we still think it's a good idea to have it. And so the same for the Helmholtz operator. So for the Helmholtz operator, you need to know the model, you need to know some attenuation, and you need to know which mesh it lives on. That's the most crucial part. And you can build it now in a few lines of code. So we've decided for this framework, because we're also interested in other meshes. So say you have a mesh that is not entirely regular, but say stretched into one dimension. So then all you need to do is you need to code up a different Laplacian, and you need to code up a different mass matrix. Okay? Well, I'm not going to show you this example because it's quite boring. All it shows you that this is a solution to the Helmholtz equation, and this would be some data recorded on the surface. But this code actually works, and I'm going to show you something else later. So how about misfit? For today, we don't need to worry too much. There are many, many options people in FWI are interested in, very robust misfits, but we will just keep with a very basic one. Just take the difference of two fields and the L2 difference, L2 norm of it. And for the regularizer, we just use some smoothness. So we just take a squared gradient norm. Okay? So this would help stabilize the inversion, which is a very ill-posed thing to do. Okay, how do we do this in Julia? Remember, by now, we have a discrete version of this objective function. We know how to solve Helmholtz equation. So for each given model, we would get the fields. We could extract the data, compare it, and then solve this optimization problem. So what we usually prefer is, or the only option in our opinion, are second-order methods. So something like a Gauss-Newton method. We also sometimes try with nonlinear CG or with the steepest descent, but that's not really practical in most cases. So you really need to know derivatives. Okay. So yesterday I had a nice, interesting discussion about this automatic differentiation thing. Okay. In this case, there's no way you want to automatically differentiate the objective function. And I'm going to show you why. So what we need is, we need some sensitivities. So sensitivities means how much does the data change when I change my model? Okay? So how to do that? So we know that if we take the gradient of the data, well, that's some linear measurements, some p transpose, of u of n. Okay, the p transpose is a piece of cake. To different, you just put it outside the brackets, okay? So that's this step. So what I'm really interested in is how does the field change when I change my model? So when I change the parameters of my PDE. Again, the model, or the PDE here, let's call it A times U, is some Laplacian of U minus some term that depends on M times U. And then the source on the right-hand side. So I'm going to walk you through something called implicit differentiation. It's a bit like torture, but bear with me. And in the end, you'll see that there's some ugly term that really prevents you from using automatic differentiation and actually from really building this derivative. Okay, so you have your linear system here. I can hit it from the left with the gradient on both sides. On the right side, you will get 0, because Q, the source, doesn't depend on M. And on the left side, what you would do is, well, the L doesn't depend on M, so that's good. And here you have one term of a product, so that's a matrix times a U of M. And then you use a product rule. Okay? Use a product rule on this guy here. Yeah, well, which will give you something. Just take a look at the last line. So when you've done everything correctly, you end up with a diagonal matrix here that has the current model, plus a diagonal of U with all the other parts of the mass matrix. You bundle things together, because remember, gradient M of U is the one we are interested in. And what you end up having is, so the gradient M of A times of A of U has two parts, something A times grad U minus some derivative of your mass matrix. You're interested in this guy, so we flip this over to the right, and we kind of divide by A. And this shows you that the sensitivity we want to have has an A inverse in it. Remember, A inverse means solving Helmholtz equation. Okay? So if you didn't get if you couldn't follow the implicit differentiation at this point, it's no big deal. All there is, when you really want to compute the sensitivity matrix, there's the A inverse. A inverse means solving Helmholtz PDE. So this will be a dense matrix, right? So you never want to have this guy floating around. You don't want to do any computations with it. And if you used automatic differentiation to get it, this would bring you into severe trouble. So what we want to do is, we never really want to build this matrix. Never ever. There's no way we want to have it in memory. But what we are coding instead is matrix vector products with it. So if I gave you a vector, it would be very, very easy for you to compute a matrix vector product. Say from the right, you would multiply it with a diagonal matrix. How easy is that? Hit it with an AV, which you have built already, and hit it with another diagonal matrix. Okay, and then you solve Helmholtz equation on one vector. But you don't want to solve Helmholtz equation on a sparse matrix as the right-hand side. Okay? And the other way around. So that's one design principle we have. And then we use a standard Gauss-Newton that takes the gradient. So computing the gradient would also require you to solve Helmholtz equations. And then in each part on the Hessian, you would also have two PDE solves. So that's about the cost. So how do we solve the system? So this will be where we spend most time. We never form HK. We compute matrix vector products. So implicitly, this is why I like handling functions to my linear solvers. And yeah, we have a package called Krylov-methods.jl, which has some iterative solvers. And we try to keep them as efficient as possible and make them work on function handles as well as on real matrices. Okay, just one thing to keep in mind. FWI is a complicated problem. It's the non-convex optimization problem. So where you end up really depends on which path you take. So I think I should show you a little bit of the code, just to. So we have another type, which is called an FWI param. And this is how I would compute the data of my PDE. So the FWI param keeps all the description of the problem. So which mesh we are using, what the frequency is, the attenuations, the sources, and the receivers. And then we would basically allocate some stuff. We would, and this will be quite important for what I want to show you now. We will build a cell array for the LU factorizations, because remember the sensitivities have an A inverse. So when we work really, really hard to solve the system, let's keep the factorization alive. That's why we write our own Gauss-Newton and not use a black box thing, because this allows us to do this trick. We get the Helmholtz operator, we factorize it, and then we loop over all the sources. And then we get the data. Okay, so that's a serial code. It's executed on one worker. I want to show you now quickly how we think about parallel computing and how we think about parallelizing for frequencies and what some issues are that we overcame. I don't need to spend too much work on this slide. It's how we think parallel computing works. It's a one-sided communication, so we are talking to the master process, I believe. There are two elements, remote references and remote calls. Well, Patrick is going to talk about cluster managers, I believe, but I prefer not to deal with that too much. And ideally, the code would work on my laptop as well as on a big supercomputer. One thing, I don't know if any of you guys has ever tried this. So when we started out, we tried to do something really innocent. So I built a matrix B. Of course, everything we are interested in is a sparse matrix. So it's a sparse random matrix. I make it symmetric and even positive definite, I believe. And then what I want to compare is I want to LU factor it on my main process. But I have two workers on my session. I want to factorize it somewhere else. Okay, why? Because later on I will have many frequencies. I will distribute all the PDEs to different workers, and they should kind of know how to factorize things. Of course, one lesson is always run your code twice when you want to time something. It's much more costly to have it on the main worker than on the remote worker. No, not, because I don't fetch the result. So it just gives me a ticket to the LU factorization. We don't have the actual LU factorization on my worker. So now, what I can do is, if I have a right-hand side, I can use LU1, that's the one on my main process, and do a backslash, right? And I can also try to fetch the LU from the first remote worker and do a backslash on the right-hand side. So what do you guys think will happen? Anybody feeling uncomfortable here? Okay, there's a fatal error. And that's one thing we couldn't really find in the docs too much, but then we figured it out and it was actually quite clear. So what happens here, what's important to keep in mind? So you do an LU factorization, which I guess pipes back to UMF pack, if I'm correct, on some remote worker. And this guy will give you a pointer. And this pointer, if you transfer it to another worker, kind of loses its context. So we have a package or a wrapper for mums, for instance. And there when you go into it, you will see that in the mum struct, there's also a field pointer, and it's not, the type of it is not a pointer, but it's an integer. And you might think that's a very dumb thing to do, but at least it doesn't crash, and you don't lose the worker. I mean, it does some other weird stuff then, but you can actually fetch things. Okay, so what I need to do is I need to write a new function, and this is something that we do all the time. We always have one function, like the getData function I just showed you, which works on like when everything is present on my worker, and then we write wrapper around it with multiple dispatch. So here would be something called solve LU, where LU is a remote reference, and the right-hand side is applied as a vector. It's known everywhere, and it would, just before we crash and lose this worker, we would check where the LU factorization actually lives. Okay? And if it lives on my ID, then I would do this. It's a no op. So the bottom line is, even if I use my whole cluster to solve or to factorize all the matrices, I will never be able and willing to communicate them back to the main process. So I have to kind of keep everybody alive, which means the garbage collector shouldn't be too aggressive on the workers, right? I mean, everything has to stay where it is, and it's my job kind of to clear what goes on. Okay, I think everybody knows more about asynchronous loops than I do, so I want to show you how we actually think about parallelizing this thing. So we think about it as a two-step process. So first, when we start out setting up our problem, we have some scheduling going on. So the main process holds all the sources, the receivers, and all the frequencies. In this case, we have 2 workers and 3 frequencies to make it a little bit interesting, but not too big. In the first step, the main process would send out frequency 1 to worker 1 and frequency 2 to worker 2. Okay? These guys are now busy, red means busy, preparing their respective forward problems. And what they would give you back is, so this guy is already done, this guy is still working. It gives you back a remote reference to the structure that contains the information on the forward problem. Like where are the sources, where are the receivers. This stuff can be deleted now from the main process. Okay? At some point, so when this guy is done, it gets the next problem. So worker 1 has now 2 problems to deal with, prepares this guy, and in the end, when everything terminates, we now have remote references to all the problems on the main worker. Okay, from there on, the assignment of problems to workers is fixed. Right? Nothing will be communicated between worker 1 and worker 2. I mean, unless there's some really big issue going on. But otherwise, we would like to keep all the meshes that were generated, all the operators that were built on the respective workers. Okay, so that's step 1. That's the setup stage. Step 2 would be how to actually solve PDEs and simulate data. So here you are given some M, some guess of your image you want to reconstruct. You have to send it to each worker once, which would be a very smart thing to do. Once they receive the model, they can go ahead and get the data, so they have to solve the respective forward problems. This would give rise, so again, worker 1 was quicker. So this would give rise to some A inverse. This would be the LU factorization we just created on the workers, and some field, which also is not neglectable in terms of memory. You don't, if you have 1,000 frequencies, or I don't know, you don't want to communicate all the fields all the time. And you only communicate back the data and the reference to everything else. And then, of course, once this guy, so it's an asynchronous thing to do, or an asynchronous loop. So once worker 1 is done with its first problem, it solves the second one. And in the end, what you have on your main process are all the estimated data and references to all the intermediates that are still alive on the workers. You don't communicate big things. That's the goal. Okay, so this was the get data phase. I could continue on what happens if you compute a matrix vector product with the Hessian. In this case, note we have the factorizations, the A inverses on the workers. So we would have the right-hand side on the main process, send it to the respective workers, each of them performing their matrix vector product and sending back an aggregated version of the, or their part of the product. So that would be the idea. Let's look at some code, how we did that. So I think I want to actually run some stuff. So I just make sure that I have some workers and that I also have a piplot. This usually takes a minute or two. There we go. So setting up a small project for us, a small problem. Yeah, there we go. So this would be the setup phase. So the setup phase, it's a get FWI param. What it would do is, so omega will be the frequencies. So the number of frequencies we have is the length of it. And then if we choose to distribute it around all the available workers, it's an interesting case, we have a sync and an async. So basically what we took as a role model was the PMAP. It's kind of a customized version of a PMAP here. And well, all the workers loop over all the problems, grab the next one, prepare them, and return a remote reference. We have just a remote call, no remote call fetch. But we wait, because we don't want one worker to accumulate all the problems. At least this is what we observed that happened at some point. Okay? And then we return an array of remote references as a description of the problem. And this allows us then to use multiple dispatch. So, for instance, let's execute this. This would be the result we are getting. So we have an array of remote references, and they are actually quite nicely, I think I had 8 problems for 8 workers, and they were nicely distributed, so each worker has only one problem to work on. And for the get data, actually we end up coding everything thrice. So we have one get data I showed you. Then we have one get data that works on an array of remote references. And we have one get data that works on one remote reference. I think we couldn't find any better way to do this. But the array of the remote reference, that's the asynchronous part. So you allocate some space for the data and some array of remote references to the fields. These are the things you don't want you want to keep on the workers, but you want to get a ticket to them. And well, you then just loop over all the problems. And the worker only gets active if the kth forward problem is stored on his node. Other than that, there's nothing going on. So let's maybe see if this does the same as the serial version. So run it twice. So yeah, the relative error is 0. That's a good thing. So the parallel and the serial code do the same stuff. And the parallel code is a little bit faster. I mean, I'm not sure what really goes on with the LU factorization, if it's multi-threaded or not. But at least it's an OK speed up. Well, we could do the same thing now for products with the sensitivities. So there's the same idea. You have one version that works on array of remote references. The reason we don't use pmap, but write our own things, rather than, I mean, except, well, no, we never use pmap, is because here we want to call the same function, getSenseModVec, on all the workers, on all the elements in the array. But some of the arguments, like the v, so this guy is always the same, but the other, only a few arguments depend on k. So we couldn't find a way to make the built-in pmap work for this kind of stuff, other than duplicating the model all and over and over again. But by now we became quite good in replicating this async things. Okay, so let's jump back to the. So I hope this gives you a little bit of insight how we think about parallel computing on a very, I would say, very basic level, probably, at least for, as compared to what I've seen in other talks here. Yeah, I showed you this example. So that's just an overview about some things that we've developed over the last year in Julia. So actually, we have an extensive library of inversion codes. We can deal with Maxwell's PDE, so electromagnetics, also with Helmholtz now. We have different types of meshes. Yeah, we have one really, so these are basically the modules we use. We don't use too many modules, and we don't use too many types. Extensive work is in the linear solvers, because we need linear solvers both for solving PDEs, that we use direct methods usually, but also we use iterative solvers for computing the search directions. So there we've worked extensively on a very modular framework, so that we can mix, solve some PDEs iteratively, some PDEs directly. And of course, we've spent a little bit work on some optimizers, some projected Newton methods, some gradient descent methods, and stuff like that. So just a quick summary. So I brushed over some basic ingredients of FWI, not spending too much time on this. A little bit on distributed algorithms. So I just want to emphasize they're mandatory for real-life problems. For real-life problems, you will have many, many sources, many, many frequencies, and there's no way you can afford the memory and the computation power on one node. So it's a really huge thing, and Julia allows us actually to do these things, also to play with distributed optimization techniques. So that would be the next step, to really explore large-scale parallel solvers. So one thing that prevents us from using black box optimization routines, we want to keep some temp results on the workers, and we want to control what's going on. That's one feature of Julia, because it gives us a lot of access with really limited demands on our side, and we want to support many architectures. And I want to highlight, Patrick is giving a talk on using some of our codes on a Cray machine. So that should be pretty fun later. Thanks for the attention. Maybe there's time for one or two questions. Other than that, I'm happy to talk to you offline.